I'd like to welcome Matt Berninger here. He's a manager on the data science team at FireEye. He's had a number of interesting roles and contributions that he's made at the company, and different ML models that he's deployed to the SOC. And he's going to tell us about an application that he's been working on. Thank you. Called APTinder. So with that, Matt, please take it away.
Yep. This is good. Thanks, Jeff. Oh yeah, gotta get close. So as Jeff mentioned, this is the APTinder talk. So I'm gonna walk you through sort of what we're gonna talk about today. We're gonna discuss first how FireEye, where I work, how we track and build up knowledge about APT actors. For those of you who don't know what APT means, hold on. That means advanced persistent threat, and that's different from like a commodity malware or financially based malware or financially based actors in the sense that they're often nation state sponsored activity that's targeted at particular targets. So that's what I mean by APT. We're going to talk a little bit about how we track that information, and then a bit about how we can quantitatively represent that information. Then I'll go into the model that we're building to sort of build similarity about those documents, and then we'll evaluate how well that analysis has worked, and some future next steps and some weaknesses of that approach and things we want to do in the future. So I'll just address the picture. This is actually, I had a different picture up until about 2 weeks ago when the FBI indicted a bunch of GRU operatives. This is Artem Malyshev. He works for the GRU, and he apparently took a bathroom selfie with his cell phone that appeared on the indictment. So for an APT Tinder joke, this was too good to pass up. So thank you, Artem, for your bathroom selfie. Quick disclosure slide. Not going to be sharing any client information. Obviously, that's pretty standard fare in the cyber industry. And there's no raw intel here. The results are real, the analysis is real, but there's no raw intel. So if you're looking for raw intel about APT actors, you won't find it here. So a bit about myself. Jeff mentioned I'm the manager on the ICE data science team at FireEye. It's awesome working with those folks. Scott and David's talks yesterday were amazing, as were all the talks so far. They've been great. Prior to that, I did incident response and endpoint detection for FireEye's Managed Defense Service, and then before that, did incident response at US CERT. I'm from DC, so go Caps. If you Google me, you will find an indie rock singer by the name of Matt Berninger. I get his email sometimes, but I am not him. I am, however, a big fan of APT data, and that's what we're here to talk about. So at FireEye, we track the adversarial activity, and we really work to identify the humans and the organizations behind those hacks. This requires a lot of data collection and investigation, and of course, that's what we do at FireEye. We do a lot of investigations. If you've ever read any stuff, in the headlines about big breaches we've worked, we do that all the time. And there's decades of expertise and experience dating back to before FireEye into government intel from people that work for us who are really good at understanding and knowing APT actors when they see that activity. And then actually in the first APT report we ever put out in February 2013, the APT1 report, which I highly recommend reading, we say that we can attribute 2 or more intrusion events to the same group when we've collected enough indicators to show beyond a reasonable doubt. And that sounds familiar. It's because it's a common legal term to sort of indicate that beyond a reasonable doubt we can make this claim. And if you read the APT1 report, I think you'll agree that it is proven beyond a reasonable doubt that that activity was all attributable to the PLA. That attribution and that analysis and that merging of data is done manually, and it's hard fought. And I will say that in my experience at FireEye, the bar for attribution is very, very high. And it takes a lot of time and effort and expertise. So like many projects, this project started with a conversation in chat with an Intel analyst that I know. And he asked me, hey, we spend so much time trying to analyze and curate and manually do this analysis. You data science guys, can you build something to sort of help us objectively do this and group this stuff a little bit faster? And I think one of the reasons for that is the number of APT groups out there is only growing. And so we are seeing more and more diversity and more targeted activity around the world. So this problem is we need to scale. So a little bit about how we track attackers. So when we see and investigate activity that we can sort of forensically link, we begin what's called an uncategorized group of data. And so I've created a fake one here, UNC 501. And when I refer to UNC groups, that's what I'm talking about. And so we put all that together, and we know that this is related because we can actually trace forensically the links between this data. So if we had an event, again, made up, that we observed someone putting SOGU on my laptop, we would mark these sort of these numbers here in these various different categories. So the method was, let's say, spear phishing. Malware was SOGU, that's a common Chinese APT malware. Target country US, and so on. And then over time, as we get more reports that are forensically linked to that activity, say it's part of a campaign, we would add more sort of terms and more observations to that document about that uncategorized group. Now we know that all this stuff is related because we know it's forensically linked together in the same operation or campaign, but we don't necessarily know who it is, or if it's part of a group that we're already tracking, or if it's a new group. And so we record this data and we kind of put it off to the side and say, okay, we'll figure out who this was later. Let's just sort of group this all together as part of the investigation. So over time, these UNC groups grow as we add more reports and more information. And eventually what we want to do is we want to really understand who this is and if they're part of existing operations. So these groups can sort of merge into each other, and then eventually we want to sort of graduate them to a named group. I've been mentioning APT groups. There's also FIN groups, if you read about FIN 7 or other FIN groups. Those are financially motivated, targeted actors. So we want to graduate that knowledge into a group that we can write a report about and share with the community. As I mentioned, the analysis is very manual and the bar is very high. So can we objectively measure this similarity? And as you're probably thinking, this turns into a document similarity problem. And that's kind of how we approached it from a data science perspective. So for those familiar with that sort of analysis, a group is analogous, or a group of activity is analogous to a document. A category here is analogous to a topic. So we have these different categories: malware, target industries, infrastructure, et cetera. An observation here, like the name of a malware sample, for example, would be analogous to a term. And then the number of times we've seen that observation would be analogous to your term count. And so the question that was posed to me by the Intel analyst was, if I have two UNC groups here and I want to know if they're similar, and should I merge them? Or if I have an APT group and an UNC group, how similar are they? So just to an analyst, we can do sort of a quick overlap and see stuff like, oh, look, they both use spear phishing. They both target USA countries. They both have Tokelau infrastructure. Fun fact, Tokelau has about 1,300 people, but is one of the largest domain registrants on the internet. And they both target the crafting industry. So spear phishing is not really a great indicator, right? Because everyone kind of spear fishes, it's really common. USA is a common target. So maybe crafting in this sense, which is kind of a joke, but crafting would be the indicator that these two groups were related. They're really targeting a very specific industry. And so that's kind of what we wanted to get at. We wanted to understand a better objective measure of similarity that we could break apart back to the Intel analyst and say, these are similar. It's not just a weird data science number. It's something you can actually understand and sort of audit mentally. So the goals of this project were to create a single but interpretable similarity metric, evaluate some past analytical decisions that maybe we've made, and then discover new potential matches. The output of this model is to give to our Intel folks, hey, here's some stuff you might want to look into. It might be similar. So before we get into sort of how the model works, this is the overarching structure. Now, people might have questions about this later, and I'm happy to answer them, but we essentially take this corpus of documents and we create similarity matrices for each one of those topic areas. So one of the nice things about this was we didn't have to do topic modeling explicitly because they're explicitly called out already in the documents. So the malware is like right there, structured, the methodology and so forth. So we create the similarity for each one of those categories. And then given those separate similarities, we aggregate them into a final similarity metric. One of the benefits of this approach, as I'll go into later, is it kind of limits the amount of impact that any given term or category can have on the total similarity. And that's kind of helpful to make sure that we're judging things fairly. So the way we converted documents to vectors, I'm not a data scientist by training. I come from the cyber realm. So for those who understand what TF-IDF is, sorry for the quick review. For those who don't, essentially it is a way of vectorizing those terms in such a way that rewards terms for being really common within the document and sort of penalizes or downweights those terms for being really common across the corpus. So the word the, for example, if you were grouping books. Most books have the word the in them relatively commonly. So that'd be a very highly weighted by commonality within the document itself. But of course it appears in almost every book. So the log of 1 would really bring that down near 0. And so that's kind of the idea here, that for stuff like spear phishing, when it's really common across all actors, we're not going to use that as a really strong term to measure similarity. So the example I gave here is if you wanted a couple documents about baseball, the word baseball would be a really useful term to use there. Maybe the word hit would also be useful, but the word the and was, they would not be particularly useful in grouping those together. So we use that method to convert those vectors to similarity. And again, we're doing this within the topic area. So APT3 malware, for example, turns into a vector of numbers that we can then use to measure similarity. So that's one thing I wanted to be clear about. So every document plus category becomes its own vector. So for example, in a world with only 2 types of malware, which would be great, if UNC201 had these values for 3-byte and SOGU and UNC59 had those values, we could represent them as those 2 vectors. And then we'd use the cosine similarity to measure essentially how parallel or how much are they pointing in the same direction. And what's nice about this approach for this particular problem is that even very small documents with not a lot of terms, if they're kind of heading in the right direction, the cosine similarity will be high, even if it's not a very large vector or a large document. And so that was nice because essentially we're trying to find those little bits of activity that might be sort of a small chunk off the iceberg of a larger APT group. So that works out well. A little bit about understanding the feature space. I mentioned sort of limiting the effect that any given term has on the entire similarity. When we first ran this, I just took all the terms and threw them into a bucket and then just did TF, IDF, and cosine similarity, treating it all as one vector. One of the problems we had was ZHCN is the language code for mainland Chinese, and it utterly dominated our feature space. And so there's a lot of high similarities across groups, which was not particularly helpful because we often, we track a lot of Chinese APT activity, and so it wasn't unsurprising, but it also was unhelpful. So by limiting it into various different categories, we're able to limit the effect that has on the similarity. And then similarly, the similarities, we want to make sure they weren't overly correlated with one another. Like if breach vectors and exploits were really correlated, we'd be double counting them, and that also wouldn't be very helpful. Luckily, we didn't have super high correlations between similarities. So we have all the similarities. We want to combine them to an aggregate metric. And this becomes essentially a regression problem where you're solving for these coefficients. I'll get a little bit more into that later, but for now, we just used a straight average. We didn't have any information to tell us that malware or methodology was worth more than any other component, so we just used a straight average. And that actually worked out pretty well. When we look at just the final similarities using that average metric, it's this exponential distribution where most groups are not similar, which at first was like, well, bummer, but it means that if we do find similarity, it's pretty significant. And so that was helpful. And when we actually measured it against merges that our Intel team had recently done, in a quarter of the cases, in the top 2 results were the ones, when they had recently merged 2 groups and we ran the analytic against one of those groups, the group they had merged with was in the top 2 results. So that was pretty validating that we were doing something right. One of the frustrations here is, for these other groups, we don't necessarily know that UNC 1023 isn't related to UNC 1011. We haven't done that analysis. So we don't kind of have the negative cases here. And so we lack labeled data. We have some labeled data, but we don't have a lot. So this was great to see, but we wanted to build a better labeled data set, and I'll go into that. The other thing we wanted to do was provide interpretability and insights. The first thing I was asked when we did this project was like, oh, we'll just cluster them and put them in a cluster graph, and then we'll just find the things. And I did that, and actually thanks to Yellow Brick, there was a talk about that yesterday. That's Yellow Brick right there on the top right. It wasn't particularly helpful. Like, we were like, look, there's a bunch in the top right, and they're probably bad, and those are probably, and there's the dimensionality reduction problem. We have thousands of dimensions essentially here, and reducing them to 2, you lose a lot of information. So we didn't find that particularly helpful. It's cool to look at, but not particularly useful. What we did find useful was breaking out those individual similarities into a dictionary there and presenting those to analysts so they could say, hey, we're merging these because their malware similarity is so high. And that kind of vibes with what they see. They're like, that's right, they do use the same malware. That's right, they do use the same exploits or whatever. The weaknesses of this approach is that, like many things in cybersecurity, it's manual data entry right now. So as we do these investigations, people are manually entering this data, and that creates noise. Stuff like marking that some groups use packers versus more granular approaches like packers that are UPX. We kind of lose granularity in various different ways that way. And then the data is temporally sensitive, and that's key. Attackers change over time, and so what APT3 is doing now is different than what they were doing a year ago, 2 years ago, 8 years ago. And so what they've done lately is probably more important than what they've done 5 years ago. we're trying and we're working on some stuff to try and represent that, but this analysis just works off of the flat information at any given time. And then lastly, I really wanted to solve that correct category weighting and really see with a better labeled data set how, what are the right weights? That really bothers me. Like straight average didn't feel right. So I did a couple things. At the recommendation of one of my colleagues, David, he gave this cool idea to take the ones that we know are similar and set their similarity to 1. And then take the ones we know are not similar, which is actually not that many, because again, we don't know what we don't know, and we don't know that two groups aren't similar until we really do. So APT3 and Fin7 are definitely not similar, because Fin7 guys got arrested a couple weeks ago. And yeah, thanks. And so we know that they're different. So we did that, but we only had a couple dozen samples. So when I trained a linear regression on that, the weights were wacky. It was way overfit, it was nonsense. So that wasn't particularly helpful. And then the other thing I did was took those same values and just did like a correlation, and then normalized those correlations to between, the sum to equal 1, so I could make that weighted average. Also not particularly helpful, suffers from a lack of labeled data. As you can see, breach vectors are negatively correlated. It's probably not good. We would like to think that our information contributes and that doesn't detract. So one other really creative idea that Jeff on our team gave me, which I really liked, was, okay, we do know, the best truth we can get from this world is, we do know that the APT groups we have classified, because we have such a high bar, and we've done so much analysis, we know that that's all one group of activity. So what if we randomly break those up into sort of false UNC groups that we pretend we don't know about, and then use the analytic to try and put them back together? And that was really cool, and I can sort of control and create as many labeled sets as I want, or as labeled documents as I want. So I did that, and it was really helpful and nice, because our analytic gave us really high similarity scores. And if you think about the cosine similarity, that makes a lot of sense. So just randomly selecting kind of just moves the vectors a little bit, but generally they're pointing in the right direction. So it was nice to see that the metric kind of intuitively makes sense in that way, and it also worked when we ran it. Every single APT group that we broke up, those randomly generated subcomponents were in the top 10 of the similarity that we generated. There's definitely more we could do here. We could fuzz it a little bit more, add some more terms, maybe completely zero out some fields that might be interesting. So we're probably going to continue going in this direction, but this was a really helpful and creative way to create labeled data where we had none. So the next steps, I really want to incorporate the time of observation. I really want to look at knowledge transfer between groups. Even though we know that APT28 and APT29 are different, we know that they're both Russian. So are they transferring knowledge even though they're different entities? Explore other visualization options, that's always good. As you saw, that wasn't particularly helpful, the stuff I've done so far. And then again, with more labeled merges, sort of solve that classification, that linear weights problem. Lastly, before questions, I'd like to just give some thanks and acknowledgements to the FireEye ICE data science team. It's awesome working with those folks. I learned something from those guys every day. Matt Peters, who I don't know if he's here, he's now at Expel, but previously my boss at FireEye, kind of got me started in this direction. Jeff Johns, who's been a great mentor. And then some other colleagues, and the MLSec project, really helpful, and secrepo.com was really awesome. And then Paul Mesterhazy, my very first boss in cybersecurity. So thanks, everyone.
Great. Thank you very much, Matt. That was a really interesting talk. I want to start off with a question that you already kind of hinted at here, which was the activity changing over time. And I'm wondering if you could say something. I think FireEye has a unique view into this problem, given the data that we've collected. And if you could say something about kind of the dynamics there, what you see, how quickly things change, and what that might do to your similarity function, and how you might deal with that going forward.
Yeah, so it's definitely a key dimension here. The information changes quickly, and we're starting to see rapid changes and increases in the diversity of APT activity. So that is something that I think will be very important. One thing that I think will be really interesting to see is malware, for example. APT actors used to be very separable by malware, at least in my experience. We're starting to see more and more commoditization of publicly available tools. And so it's akin to if you're using ballistics to sort of do attribution in a crime. If everyone starts using the same gun, that attribution gets a lot harder. So it'll be interesting to see if that's happening. And that's one thing I'd really like to see is as more and more tools become publicly available and commoditized, are we going to start to see some more blending in the malware or methodology categories, and what other categories are going to be those now separators? So I think that'll be really interesting to work on.
So for APTs, there's often like counter attribution techniques they can use where they just lift code from some other group. Do you try to attempt to account for that at all, or it's obviously a really hard problem, right?
Yep. So that was one of the reasons why I wanted to limit the effect that any particular category had, because if there was, and we have seen that, we've seen groups pretend to be other groups. Sometimes it's sort of an info operation where they put up a social media account or some public account and say there's somebody else doing this for some other reason. Making sure that we have a diverse data set going in where we're looking at infrastructure and methodology and things that are harder to fake, that gives us sort of, I think, more robust and less brittle attribution, because it's easy to just grab malware out of a forum. It's really hard to fundamentally change the way you do your operations. So yeah, good question.
I hope to understand your data a little bit better. So because some of the APTs actors may be merged in the future, later,
Yep.
They might be different groups. So if you go back, today, if you go back 5 years, whatever years, that you might find some activities that was labeled like 5 years ago for this APT. Now we know this actually belongs to the same APT. First is, do you have that kind of data? How would you view that kind of data in terms of that activity was actually supposed to be this merged APT instead of the APT from before? How would you treat those data?
So just to understand your question, it's if there was something that was labeled as one group before, but now we know that to be a different group?
Different group or merged groups.
Oh, got it.
So if you go back to look at that, how would you treat that activity that was done 5 years ago?
Yep. So that'd be more of an Intel question, frankly. That'd be something our Intel team would probably handle in how we are categorizing that activity. That's certainly a possibility, though, right? I mean, organizations are always changing and reorging and stuff, and these are real organizations, government organizations that are going to make changes. So we would probably say, that APT group or that group of activity has been, degraded to some extent, and now that activity has moved over here. But that's more of an Intel question as how they would represent that. For the purposes of this analysis, that would be something that using a flat analysis would suffer from. But if we were able to incorporate that time aspect and sort of run this maybe, say, every day or every week, we would then be able to draw a line in time and say, well, everything before then doesn't really matter for this group. Everything now, from this time on, where we make our Intel assessment when that merge happened, that would give us the ability to make that distinction.
Hi, thank you. That was super interesting. I was curious when you were talking about, you mentioned that you looked for correlation between some of the different spaces or some of the different dimensions you had. Did you experiment with principal component analysis to both to get rid of that correlation and also just from curiosity to see which dimensions, like maybe people who use the same methodology always use the same, I don't know, malware or whatever?
Yeah. So out of curiosity, so I'll answer the first question. Yes, because it kind of made sense at first, but it's really hard to explain to an analyst, like eigenvalues. So the methodology values kind of get you over here. And so that made it less interpretable, essentially. So that's why, for the purposes of this analysis, and actually under the hood, there's a lot of sub-functions where you can query the similarity and sort of see Jacquard similarity, for example. That might be another way to show, why they're similar. Because even the cosine similarity thing gets a little bit mathy for folks. So yeah, that's why for the actual service, PCA isn't used. But from a sort of investigative standpoint, I did see stuff like breach vectors and comms vectors start to sort of run together in various different ways, and that was kind of interesting. I don't have a whole lot of good answers there, but I'd like to investigate that further. Again, the time thing sort of feeds into that.
Matt, this may be a question for the Intel group, but I'm interested in your thoughts. But so you now have a similarity function, and now you can say for this shred of evidence for this new UNC group, he is this percent similar to each of these groups. Is that useful for an analyst to determine at an earlier stage winnow out which groups they are, even before making a determination, but sort of a gut check earlier on?
I think so. I wouldn't want to. That's a really good question. So there's two analysts in this equation, actually. There's an intel analyst and there's an incident response analyst or an incident response team. For the incident response use case, having been on that side, I found that attribution is super helpful if it's right. So if you're running an IR and you find out, you're running it and you're grabbing malware and you're grabbing, artifacts, and your intel, so the person who's detailed to you from the intel team says, oh, we definitely know it's this group. That allows you to then pivot to a bunch more indicators that can really speed up your analysis. So you're like, oh, okay, well, I'll just grab all these other malware indicators, throw them against the network, and boom, 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 backdoors pop up everywhere. So if that's really helpful if you can get that really confident attribution early on, because it can really speed up your investigation. I wouldn't want to pigeonhole an intel analyst with this analysis and say, it's definitely, that's one of the reasons why the distribution was so helpful, because we really want to have high confidence if we're going to have similarity, because you wouldn't want to waste a lot of time going down a rabbit hole just to find out, hey, we should have looked over here. So it's a tough question to answer, but there are operational benefits to making that decision early in the game.
All right. Let's everybody thank. Oh, we got one more? Yeah, go ahead. I think we have a minute. And Wallen, if you want to start.
Thanks. So I'm not a cybersecurity expert, so just curious. Okay, so you mentioned that so those APT groups have certain kind of operations, right? That are hard to change. What if you know how they operate, right? What if you are a group that knows how another group operates? You can probably pretty easily fake the other group operations. You just say, you got 5 guys, this guy does that because operations says that he does whatever, I don't know, downloads something, and so on and so forth. So how could you possibly distinguish between them?
That's a fair question. It's kind of unanswerable, but I would contend that it's not that easy to fully replicate the way another group operates, from building new infrastructure to building new personas to completely doing things differently. One of the things that really comes through is like knowledge of language, for example. So you'll see mistakes, you'll see sort of tool marks and trademarks like that I honestly, in my experience, are really hard to fake. Now, granted, one of the things that will help with that is as people commoditize their tools more. So for example, if I was an APT actor and I knew that these folks over here use a lot of commodity off-the-shelf tools, that makes that replication a lot easier. If what the other group that you're trying to replicate does is very customized, that makes it more difficult. It's certainly a possibility. I don't know that we've seen a whole lot of that complete fake stuff. And honestly, the other thing is, how important is it that they fool the right people? To use sort of a Russian tactic, it's not that they need to convince us that they're a different country. They just need to cast enough doubt on the attribution that people could say, who's to say? If you cast enough doubt on that attribution claim, you don't have to convince that you're somebody else. You just have to sort of sow doubt in that attribution. And that works well enough, as we've seen recently.
Great. Thank you very much. Let's thank Matt again.